All right, and objective 2, we've got a picture that seems kind of tilted a little bit. It's tilted because, well, you see there's a reflection right there. And we've talked about reflections across that diagonal line, so essentially y equals x. What does that give you? That gives you inverses, and that's what this objective is about, is being able to find the inverses of logarithmic and exponential functions. Okay? And it should be a piece of cake. Look over there at the flipping math logo, because we can see in the flipping math logo that the inverse of an exponential is a logarithm. And, if I say that the other way, the inverse of a logarithm is an exponential, right? So, this first exercise, we're doing that function composition thing. You remember this, where we stick a function inside of another function. So the first one that I want to do is g composed with f of x. So I'm sticking f of x, this function, in here. And see what happens. So I get the log base b of b to the x. Do you remember one of those properties you wrote down from the first objective? This is equal to x. What happens, or like, why is that significant? Whenever you do the composition to two functions and you get x back, what does that mean? It means that they're inverses. Remember something like this. If I were to take the cube root of x cubed, I get x back. So that's what these are saying, is if I take the log of that exponential, I get x back. Okay, so if I do this in the opposite direction, and writing g down is not the opposite direction, there we go. F composed with g of x. Now I'm going in the opposite direction, and I'm going to put b, and the exponent is going to be the log base b of b, no, of x. That should be equal to, well, just based on what we have already seen, it must also be equal to x. This is going to be another one of the inverse properties. These things are inverses. So here are the two inverse properties. By definition, we're saying that logarithmic functions are inverses of exponential functions. So over there on the left-hand side, this is a property that you have already written down. It was an exponential property. So the log base b of b to the x, those things cancel each other out. Like I said, it's like taking the cube root of x cubed and I just get x back. Okay, over there on the right-hand side, since a logarithm is an exponent, if I take b raised to the log base b of x, I get x back. I have just undid what I did. Those things are inverses of each other. So get that new one down as well. And let's apply that to these problems. So in exercise 8, what is e raised to the natural log of 9? Remember, natural log has a base of e, right? It's a base of e. So these things are inverses of each other and they cancel each other out, and I just get 9 back. Look over here at number 2. The log base 3 of 27 to the x. This one's a little tricky. It's a little tricky because you have to rewrite the 27 because it's not a power of 3. If I look back at the property here, this thing that's inside the property has to have the same base. Has to have the same base. Okay, so can we rewrite 27 with the same base? How about the log base 3 of 3 to the third power of x? Now let me just rewrite that one more time and make that the log base 3 of 3 to the 3x. Alright, now everything should cancel out. And what I should get back is just the exponent 3x. Okay, so the next thing is about actually writing the inverses of some functions. And I've got two things that I have to do. Maybe I'm writing the inverse of a logarithm, or maybe I'm writing the inverse of an exponential. So the first one, well, in either case, remember the first step is always to take your x and your y and you swap them, because that's what inverses do. So step number 1 I'm going to switch the x and y. Now, if I'm finding the inverse of a logarithm, after I switch x and y, rewrite that equation in exponential form. Okay, switch x and y, rewrite the logarithm as an exponential. Okay, if I have an exponential and I'm trying to find its inverse, first switch the x and the y, and then rewrite it in logarithmic form. There it is, right in logarithmic form. So when I'm writing the inverse of a logarithm, I write it as an exponential. When I'm finding the inverse of an exponential, I write it as a logarithm. Let's try that right here. Okay, find the inverse function, and on the first one, it's an exponential. So since it's an exponential, how am I going to write the answer? I'm going to write it as a logarithm. First step, though, is to switch x and y. So this becomes x is equal to 8 to the y plus 3 power minus 5. Now let's isolate the exponential part by adding the 5 over to the left side. So I have x plus 5 is equal to 8 to the y plus 3. Now I have something that I can write in exponential form. The base of that logarithm is going to be 8. So I could write the log base 8 of, and whatever my answer is to the exponential equation, that's this one, I put in x plus 5 inside of it. And the exponent on an exponential, that is the answer to a logarithm, y plus 3. Okay, one more step. Let's subtract the 3 over to the other side, and I get log base 8 of x plus 5. That part's in parentheses, and the minus 3 is outside the parentheses. It's equal to y. All right, and I don't like it in that order. I like y first. You like that too? Yeah, probably. So y is equal to the log base 8 of x plus 5, close parentheses, minus 3. There it is. Here is the inverse of that exponential equation. Just take a look at the variables. Take a look at what, like the constant numbers, where the 8, the 3, and the 5 are. Look at their signs. There's some kind of pattern there. Okay, number 2, write the inverse of this logarithmic equation. How am I going to write the inverse of a logarithm? As an exponential. So first step, though, is to switch the x and the y. X is equal to the natural log of y minus 4 plus 2. So we have to isolate the logarithmic term by subtracting the 2 to the other side. X minus 2 is equal to the natural log of y minus y. What's the base? Remember, the implied base on natural log is e. So e raised to the x minus 2 power, because the answer to a logarithm is always an exponent, is equal to y minus 4. Get the 4 over to the other side by adding it, e to the x minus 2. This is not part of the exponent, plus 4 is equal to y, and then just switch sides to make it look pretty. Y is equal to e to the x minus 2 plus 4 power. No, not plus 4 power, just plus 4. Again, look at your original equation and its inverse, and there's some sort of pattern there with the numbers and stuff. Okay, so if I'm not missing, no, one more slide here, and that is this, something, an important distinction to make. So we said that in the definition of a logarithm, that it's equivalent to an exponential. We also said in the course of this that the inverse of a logarithm is also an exponential. And here's the difference between how this is written. Right in the middle I have a logarithmic equation. Y is equal to log base b of x. Rewriting that in exponential form. So these two things are equivalent. Over there on the left-hand side, the base is b. Okay, so the base is b, the exponent should be y, and the answer should be x. And that's exactly what it says. So x is equal to b to the y power. Now, How do I find an inverse? I take the x and the y and I switch them. So look over there on the right hand side. It just switches the x and the y, and so it becomes y is equal to b to the x. So these two aren't equivalent. That's the inverse of the logarithm. So now that'll finish it. And the next one we're going to do just a wee bit of graphing.